So in the last section, we had this algorithm for decision tree learning, but we left out a critical part, which is deciding how to choose the correct attribute. The idea behind choosing an attribute is we want to find one that splits the training set into subsets that are ideally pure, in the sense that they're all positive or all negative in the case of binary classification. Let's look at this in practice. Let's say we have this problem of deciding which restaurant to go to. Here we have 12 different instances that we've made our decision about, whether to choose a restaurant or not, based on particular values. For example, we might decide what restaurant to patronize by looking at whether there are enough customers in the restaurant or not. For example, if we know there's no one in the restaurant by peering through the window, we might decide that that's not a restaurant worth going. If it's full, we might decide to wait or we might decide to go, but most of the times we might decide to take the restaurant if we see some people eating there. On the other hand, we might decide on the type of cuisine. We could pick between French, Italian, Thai, or burgers. Here we would decide that patrons is a better choice. Why would we say that? We can see why, because, at least in the case of none and some, the remaining problems are finished, in the sense that for none, we are always not going to visit the restaurant, and then for some, we are always going to visit the restaurant. If we look at type here, we can see that it doesn't help us at all. In fact, even if we decide what cuisine to pick, French, Italian, Thai, or burger, we're still as clueless as before whether we're going to decide to visit the restaurant or not. So the purity of the subproblems is what we're after in choosing an optimal attribute. So how do we actually pick this feature? We're going to implement the choose attribute algorithm in decision tree learning for enumerated feature sets. Let's say this particular attribute that we're examining has C possible values. We'll first need a concept of how we're going to measure the purity of the subsets. We can appeal to information theory and use the idea of entropy, which we'll denote as h of x, which is simply the probability times the log probability of the particular class. So here, these p stands for probability. For an example, if we have just positive and negative cases, we can use P to denote positive examples and N to denote negative examples. In this slide, this bottom half of the slide just counts P as the number of positive examples, so don't confuse it with the top part. So the entropy of these two cases is basically the fraction of positive examples, fraction of negative examples, and then summing together the negative of the probability times the log probability of each of the classes. Here's the case for the positive one, and the case for the negative one. We can understand this as a measurement of entropy. Entropy is basically the number of bits that I need to send you to encode some information. For the case of a positive proportion, the binary two-class entropy is graphed as the one on the right, where we can see we would have no information to transmit if it's clearly the case that all of the examples are negatives. It would also be 0 in the case where all of the points are positive examples, because I also don't have to tell you anything. It's just purely transmitting all of the instances as an expected value of 1. However, we're maximally unsure when half of the examples are positive and half of them are negative. There we need to encode each example with 1 bit of information, because it's maximally unsure of whether I have a positive example or negative example. As the proportion of examples goes between 0 and 0.5, entropy grows, and from 0.5 all the way to 1, it works in the reverse fashion, so it will go monotonically down to 0. That helps with the idea of calculating the purity of a particular set of examples. Now, how can we incorporate that to measure which attribute should be best? The idea behind this is that the chosen feature that we want to divide the example set of instances on into subsets should try to reduce the entropy of the remaining subproblems. So if we have the entropy of each particular resultant subset and we have their proportion, we can calculate the remainder of information left in the problem as basically the sum of all the individual subproblems. So then when we want to measure the information gain, in other words, the reduction in entropy, we want to choose the attribute that has the largest amount of information gain, which is basically how much information there is in the problem, subtracting from what is remaining after we split on xi. This is our information gain for the particular set of examples when we choose the feature xi to split on. With that in mind, let's revisit our restaurant example. For the training set based at the root, we actually have 12 examples that we're going to look at. And all 12 of these examples are evenly split between positive and negative cases, 6 each. So the entropy is maximal with an entire bit of information that needs to be expressed when transmitting this information. When we consider the attributes of patrons and types, we can calculate the information gain, which is basically the information in the basic problem minus what's in the remainder, which is here. Let's go through the remainder calculation for the case of patrons. Here we have 2 out of the 12 examples, but the entropy is clear. They're all negative examples. Here in the middle case, for some, we have 4 examples, but again, all of these are positives, so it is also a case of no entropy remaining. The only case that does have information is the case where we have 6 examples that are 1/3 split as positive cases and 2/3 split to negative cases. This results in some reduction in the information in the remaining problem of 0.05 bits of information. Let's contrast that with splitting on type. With type, we split it into 4 categories: French, Italian, Thai, and burger. But the problem is each of these separate subproblems are all tied at 50% each, meaning that they don't add any information. All of the subproblems are cases where they're maximally unsure. So the resulting sum here is all 1. And when we subtract 1 from 1, it equals 0 bits of information. So actually splitting on type doesn't help us at all. So in this case, if we only have these 2 attributes, it's very clear that patron has the higher information gain and would be chosen by the decision tree learning algorithm as the root.